Good day, ladies and gentlemen. My name is Irina Bannikova. I am presenting a paper, Scaling Laws in Fragmentation Dynamics of Rock Materials. The work is carried out in the Institute of Continuous Media Mechanics, Ural branch of the Russian Academy of Sciences in the Laboratory of Physical Foundations of Strength. The work was carried out with the financial support of the Russian Foundation for Basic Research. The fragmentation process exhibits the signs of a critical phenomenon and corresponding scaling laws. The analysis of the material behavior is carried out depending on the load energy near a certain critical point, which corresponds to the transition from a damaged material to a fragmented material. The critical behavior in fragmentation are investigated by analyzing statistical fragment distributions depending on the material properties, ductile, brittle, its initial structure, porosity, load intensity. Scaling analysis of spatial temporal data of fragmentation samples of sandstone in order to determine the spatial invariance of the fragmentation process of a low-modular rock to of interest for geophysical applications. The first attempts to describe the fragmentation statistics of cylindrical shells subjected to shock wave loading were made by Professor Mott. Mott believed that destruction was instant. He didn't consider the resistance to the fracture in the rupture point and the corresponding destruction energy in the rupture process. Mott argued that the destruction energy was negligible. He assumed that the statistical nature of the destruction process is determined by the characteristic fragment size and the fragment size distribution. The aim of this work is experimentally study of the cylindrical samples from quartzite fragmentation based on the study of the laws of fragment size distribution under conditions of quasi-static and of dynamic compression with joint registration of fractoluminescence. That will contribute to the establishment of a relationship between the self-similar laws of deformation and of fracture with multi-scale mechanisms of the structural relaxation caused by the behavior mesoscopic defects. For testing there a rock, quartzite, containing quartz, which has piezoelectric properties, were selected. The parameters of quartzite are presented on the slide. The bases of the samples were polished on multi-abrasive silicon carbide paper in water to shine. Tests of specimens were carried out on an electromechanical universal testing machine performing uniaxial quasi-static compression and on the Hopkinson-Kolsky bars installation that fulfills the conditions of dynamic loading. Fractoluminescence was registered by two methods. In the first, the joint operation of a photomultiplier and oscilloscope was used. In the second, a high-speed video camera was used, which recorded the destruction of the sample and fractoluminescence. Photos of the setup and the equipment used are presented on this slide. The cylindrical sample was placed in the center of the loading machine platform. Synchronization of the camera and loading start was carried out manually. The parameters of the sample and the loading rate were set in the settings. The loading machine stopped automatically when the sample was completely destroyed. Consider the case of dynamic loading of cylindrical quartzite. Air is pumped into the high-pressure chamber with the help of a pump to the 5 atmosphere. After opening the valve, compressed air accelerates the impact along the barrel. After the impactor collides with the input rod, the compression wave is excited in the latter. The compression wave is transmitted through the rod to the sample 8, after which, due to the difference in sound impedances, the wave decays into the wave that passed through the sample into the output rod and into the reflected back into the input rod. In the interface of the loading machine was recorded data on the dependence of the loading force on the plate movement as are shown in figure 5. For example, Fourth sample, the first part of the signal corresponds to the formation of cracks in the sample, at which the sample has not yet collapsed. The second, additional loading and complete destruction as shown in the photo for sample 2. A photomultiplier was used to record the luminescence of the sample, number 1, in the process of uniaxial quasi-static fracture. The destruction was accompanied by single signals and multiple impulses. This is typical for the main crack's initiation in the sample and complete fragmentation it. With the help of a photomultiplier, the luminescence of sample number 3 was recorded in the process of dynamic destruction. The destruction was accompanied by a signal with multiple pulses. This is typical for destruction with the appearance of micro damages and their merging into macro cracks until complete fragmentation of the sample, followed by the fracture of the fragments themselves. The form of the fracture process under dynamic loading was similar to that observed the fourth sample under quasi-static loading. The slide shows frames from the video recording of fractoluminescence of 4 samples in the destruction process. The video camera recorded single flashes correspond to the initiation of micro damages in the sample, prolonged luminescence corresponding to macro cracks, and subsequent single flashes correspond to the destruction of fragments. The results are comparable to the signals from the photomultiplier. The resulting specimen fragments were identical in shape and size regardless of the loading conditions. Sample fragments were sieved across sieve system and weighed. The total number of fragments was counted on each sieve. On any sieve under consideration, there were fragments, the shape and size of which are characterized by similarity. The weight of the fragments was 98% of the initial sample mass. This slide shows the cumulative fragments distributions for 2 samples obtained under quasi-static, number 2, and dynamic loading, number 3. The curves have 2 slopes. Each slope is described by a power law, which is typical for the destruction of brittle materials. For large fragments, the power in the law was the same for all samples. For smaller fragments the degrees were different. Part of the curve runs below. This is possibly related to the formation of these fragments as a result of the large fragments break. And in conclusion, the results of the work are shown on the slide. Thank you for your attention.